Right now, we have to compute the indefinite integral of z cubed times ln z dz. So, first of all, we can notice that our variable isn't x or t or any of the variables that we're used to, but that's okay because we can integrate with respect to any variable. The variable really doesn't matter as long as it's consistent within itself. So first of all, we'll take a look at this integral and notice that we can't easily use substitution for this or any other sort of integration trick. So we can see that this is a product of two functions. So one of the newer tricks that we learned is integration by parts. So let's try that. Now, do we want to differentiate z cubed, or do we want to differentiate ln of z? So what the goal of integration by parts is to get rid of one of the terms. So if we integrate, or if we differentiate ln z, what we're going to get is 1 over z. And then if we keep differentiating that, well, we're just going to get higher and higher powers in the denominator. Whereas if we differentiate z cubed, then maybe eventually we're going to get to 0, or we're going to get to some form which might be easier, since these powers will decrease each time we differentiate it. So let's give that a try. We're going to set u equal to z cubed. Du is equal to 3z squared dz. So we just differentiated z with respect, or differentiated u with respect to z. And we're going to let our dv equal to ln z dz. And right now we have to integrate ln z. So this is a problem in its own. So v is going to be equal to ln z dz. So if we want to integrate ln z dz, one way to do it is by parts again. So we're going to use some different variable names instead of u and v because we used those already. So let's use w. So we'll let w be equal to ln z. dw is going to be equal to 1 over z dz. And let's have our second part be x. So we'll call dx equal to dz, and x is going to be the integral of dz, which is just z. So what integration by parts says is that if you have a function here, or if you have this integral here, that's composed of u dv, what this is equal to is uv minus the integral of v du. So what this essentially is product rule. So if you move this to the other side and differentiate, all you get is product rule. So we're going to do exactly just that, and this v is going to be equal to these two multiplied together. So z ln z minus z times 1 over z, which is just the integral of 1, or the integral of dz. And we know that that is z. So if we write this in simplified form, then what we get is z ln z minus z. And you can put a plus c here, but we're going to do that at the very end. So now that we have our uv and our du, we can go back finally to our original integral and do our substitutions. So we're going to integrate by parts. We're going to multiply u and v together. So what we are going to get is z cubed times z ln z minus z. And then we're going to subtract v du. So we're going to subtract the integral of v du. So that's 3z squared z ln z minus z. This is respect to z. So if we take a look at this integral, oh, this is supposed to be a squared, not a cubed. If it was a cubed, it would no longer be possible. So if we take a look at this integral over here, this, we can sort of see some resemblance to our original integral. So maybe we can move that around, or maybe we can move it to another side, perhaps, and then we'd be able to cancel things out. So let's simplify things. Here we're going to have z to the fourth ln z minus z to the fourth. And here we're going to subtract the integral of 3z cubed ln z minus 3z cubed dz. So now we can separate these two integrals. So we have this over here, which stays the same. And here we can have one integral, which is negative 3, the integral of z cubed ln z. And then minus minus becomes a plus. So we have plus the integral of 3z cubed dz. And these are all with respect to z. So what we can do now is find some more space. What we can do now is just copy down everything we had before. So z to the fourth ln z minus z to the fourth minus 3 times the integral of z cubed ln z dz. And this is going to be plus 3 times the integral of z to the cubed dz. And notice that this right over here is 3 times our original integral. So if we go back to here, we can see that our original integral over here is the integral of z cubed ln z dz. And if we call this something, perhaps if we call this I, whoops, okay, we need to show the layer. Here we go. If we call this I, then we have this entire thing over here equal to I, because this is what we were trying to find. And here we have negative 3I. So this is negative 3I. So this is our initial integral times negative 3. So what we can do now is we can move this to the left side so that we get 4I. So we have 4I equal to z to the fourth ln z minus z to the fourth plus 3 times, and the integral of z cubed is just 1 over 4 z to the fourth dz. Or dz, there's no dz, it's plus an integration constant. So right now we have this, and you may think this is like a non-legit way of doing things, but this is perfectly okay because this is exactly what we started with. So if we replaced I with the integral of z cubed ln z dz, then we would have 3 of these, or negative 3 of these on the right, and 1 of them on the left. So we can just move this to the left to get 4 of them. So the answer to our integral is, in fact, this entire thing divided by 4. So we'll have 1 over 4 z to the fourth ln z minus 1 over 4th z to the fourth plus, so 3 over 4th becomes 3 over 16. And then this is going to be z to the fourth plus an integration constant. Now, this can still further be simplified. So if we have negative 1 over 4 z to the fourth, and we add 3/16 z to the fourth to it, well, then all we're going to get is this, putting this in terms of the lowest common denominator, it's going to be 4 over 16. So we have 4 over 16 z to the fourth plus 3 over 16 z to the fourth, and this is negative. So what we get as our final answer is 1 over 4th z to the fourth ln z minus 1 over 16 z to the fourth plus c.